I'd like to give a small introduction to machine learning and artificial intelligence. I would like to ask how many of you have any understanding of artificial intelligence, neural networks, or machine learning? So, a few hands. Great. So, I've been always fascinated by AI. The concept that there could be a machine thinking just like a human would was really exciting for me. And of course, I wanted to know all about it. So I've started to learn, I started to read, I've read a few books, and I still didn't really understand how it really worked. I knew the concepts, but didn't know the details, couldn't really use it. So I've spent almost half a year in an online course on Coursera, specializing in deep learning, led by one of the best researchers in AI, Andrew Ng. It was a really cool course, and I was able to really implement a system for machine learning from the mathematics up. So, what is an artificial intelligence? During this path, I've come across a funny notion about the AI effect, which can be summarized as that the AI is whatever we cannot do yet. Because when computers can really solve some problems, for example, chess, then it's no longer an AI. It's just a computer doing chess. The same thing is with computer vision. Today, computers can really understand what's on the road, can understand how far is a next vehicle, can really avoid obstacles, etc. And we don't continue to call this artificial intelligence. Or at least not everyone does call it artificial intelligence. So basically the AI is whatever comes next. It's not what we have today. And this led me to neural networks, because neural networks are a part of machine learning, and it has a strict definition, which is not something in the future. It's something that can be really now. So it was more interesting to learn about neural networks. Well, basically, it's it's not that hard. The maths is pretty simple, actually, and it's been known since the 40s. This is something that really surprised me, because I thought that neural networks are just like this century and that's it. But it's here almost for like 80 years. What is interesting is that a neuron, a base unit of the neural network, has several inputs and has one output. Does anyone know anything about biology and neurobiology? No? Okay. I'll skip that then. Other than the inputs and outputs, which are just real numbers, so you can really imagine 2.5 here and 1 here and 3 here. It's not some vector. It's not really hard. It's just numbers. And then in the heart of the neuron, there is a weight for every input. There is one weight, still a real number, and one bias. And there is also one activation function, which we can talk about later. And as you can see here, this is a little tiny bit of mathematics, which is basically saying that you can get the output, the y, by multiplying x1 with the weight 1 and adding x2 times the weight 2, etc., for every one of the inputs, and then adding the b. And then pass this whole through the activation function, and you get your y, your result, your output. This is really just adding and multiplying, which we all know. And the only mysterious part here is the activation function, which can be really also very simple. Here you can see 3 main activation functions, which can be pretty scary if you look at them and hate mathematics at the same time. But they are not really so mysterious after all. You can look at this. This is just the max OX, as you can see here. It's basically just you take the positive part. If the number here is positive, the y is the number. And if this number here is negative, then y is 0. This is a really simple function. And the functions are used basically for 2 things. They can bound the output. So if you need the output to be, for example, between 0 and 1, for example, for outputting a probability of some effect, then you can use this function, and you will always know that the output will be between 0 and 1. And the other important part is that without the activation function, the whole neural network could be simplified to a polynomial function, which can be interesting for mathematicians here, but for probably no one else, so I'll just skip it. And the neuron has this interesting property that it can learn, because it can iteratively correct these numbers, just these numbers, and it can, by this process, it can modify the output, so it's slightly better for the training data. And over time, with thousands of iterations, for example, it can give you really precise data. It can give you really precise predictions. And if you just put these neurons into layers and you connect adjacent layer, so you just wire the outputs from one neuron to the inputs of the neuron in the next layer, and you do it multiple times, you get the network. And basically, only the first layer, the input layer, and the last layer, the output layer, are interesting when you look at it from outside. These layers in between are considered hidden, and then they just function as a black box. You just simply don't have to know anything about it, and you can still make the system work. You can still teach it something just by showing it data. You basically feed it data, and by some pretty interesting mathematics, it just corrects the weights and the biases inside each of these neurons. And after time, it can give you a really exact predictions based on pretty complex matters, like speech-to-text recognition, like image detection, etc. It can even read the captchas for you. Even if you can't do it, the neural networks can. They are much more effective at reading captchas than people are. Pretty interesting. And the networks can get pretty big, like tens, even hundreds or thousands layers in the extreme examples. and even millions neurons in total. They can get pretty massive. So what is important is the design of the layers and the way they are connected. That's what makes it work. That's what's interesting, and there are some special tricks how to make it work for sequential data, for big images, etc. But as I promised, I won't get into details in this talk. We can talk about it later if you want to. But I just want to summarize what can it be used for. So it's basically anything that you can encode in real numbers. So if you have some real numbers around you, or maybe characters, maybe text that can be really simply encoded into real numbers, you can use machine learning and learn some interesting stuff about it and make some predictions. It can even generate literature. It can even generate articles about sports. It can even read them. If you want to extract some meaning out of the text, neural networks are a great way to do it. So it's very efficient at detecting patterns. Even if you don't see the patterns in the data, neural networks can do it and can extract the meaning out of it. They can do speech recognition and synthesis. They are so good that at Google, at DeepMind, they actually made an artificial intelligence system that really called a barbershop, I believe, on behalf of a customer and made a reservation there. And it really interacted with the person, and the other person didn't even know it's talking to a bot. It even mimicked as a people when they need a time for thinking. I tend to do it a lot. They do this sound like, I don't know, and the neural network just gets some time to process the answer using this clever trick. It can also do object detection. As I talked about autonomous cars, it's a really important thing that it can detect objects such as pedestrians, cars, traffic lights, etc. It can do face identification. It's so good and so cheap and so effective that you might even have a mobile phone that is just unlocked by you looking at it. And it can even play games like chess or Go, or even StarCraft. Really, you name it, they can play it. So here is the object detection. This is a YOLO algorithm. It can really fast in like real life, real time. It can detect all these objects on a standard laptop. It can detect cars, bicycle, people, traffic lights. It can be used for generating images. Right. It can be also used for generating images. This is the deep dream, almost psychedelic-like images that were generated by neural networks that were just amplifying what they saw in the image iteratively over time, and these awesome images came out of it. This is just a neural network that is really trying to see images that weren't really there in the original image, and they are just filling in the little details iteratively, one by one. And it can also play games. This is the architecture of the StarCraft API that was used for a neural network to play. This is a screenshot from the recording of AlphaGo that beat the human grandmaster and officially officially made the machines win in this game. And this is Mar.io, a little neural network that is playing Mario better than any living person on Earth. So, if you want to start with machine learning, this is a really great time because there is such a lot of quality resources available. There are whole frameworks and libraries, so you just don't have to really understand the little details of the mathematics. You can just pick up a library, pick up a framework, and start designing your neural networks. There is a ton of literature and papers on the topic. Machine learning guys are crazy about open source, and they are like publishing everything transparently on the web. And I'm not a person that would read scientific papers for fun, but machine learning is one of the topics that is really interesting, and the scientific papers are actually approachable. They are not so hard that you cannot understand it. It takes a bit of time, but you can go through it, and it's pretty interesting. There is also a lot of online courses, for example, on Coursera. There are even APIs, so you don't have to implement anything. You just use Watson API and just use it as a service. Or there are also trained networks, so you don't have to train your own network, you don't have to design it, you just get it from GitHub and use it. But not everything is fine and dandy, because neural networks typically need a lot of data. It's a good thing that this can be mitigated by using a pre-trained network, because you can really download a new network from the internet, and using neural transfer, you can even use it for a slightly different use case. So, for example, these guys wanted to detect cancer in the medical scans, but they didn't have a lot of data. They had just like hundreds of these scans with the cancer cells highlighted. So they downloaded an already trained network that could detect images like cats and dogs, etc. And they just retrained the last part that detected the actual features hidden in the data, and retrained it to detect cancer cells in medical scans. And they just used their hundreds of images. It's doable, but usually it needs a lot of data. There is a big danger of the black box, because, as I said, you are interested only in the output and the input. You are not interested in the hidden layers, and in fact, at the moment, it's not really possible to understand them thoroughly. So when you build a system that is important, that makes important decisions, it's pretty bad that you don't know why it made those decisions. So there can be really another danger with biased data, because if you feed the system a data that is, for example, racist or sexist, like most of our data today, you can get a system that treats, for example, women and men not really in a balanced way. For example, a system that were used to detect meaning out of the text, and it could make associations. It, for example, made a pretty strong association between woman and a nurse, and between man and a computer programmer, for example, which is based on the data we have today, but also it's sexist, right? It shouldn't be acceptable. But in neural networks, this is hidden in the black box. So if you get biased data, you get biased results. It's pretty straightforward, but it can be a big problem. Also, the neural networks can behave pretty unintuitively. For example, it learns that a cat, when an animal has 2 pointy ears, it's pretty probable it's a cat. So if it has 7 ears, maybe it's more probable than it's a cat. And that's not pretty intuitive, right? If it has 7 pointy ears, it's pretty sure it's not a cat. So, and it can be fooled. It can be fooled, and it is connected to the unintuitivity of the neural networks. For example, these are several images that were specifically engineered to evoke some a very strong conviction. Then, for example, here the neural network was like 100% sure this is a soccer ball. The neural network was almost sure that it's accordion. This is a pedal, and this is an assault rifle. Try to imagine if you walk around in a shirt with this pattern, and then some police robot just tackles you down and arrests you because you are having assault rifle with you. This is pretty scary when you think about it. But these images were specifically engineered just to highlight this problem of the fooling. And in the original paper, there were even just images that looked like white noise. And even though it looked like white noise to human, the machine was convinced that there is some image. And this is pretty dangerous, for example, with the face recognition. Because if you walk into a building with a paper with some unrecognizable pattern, and you just go along and pull it out for a camera, and the camera is convinced that you are someone else, this can be dangerous in a real-life usage. So there are some disadvantages, there are some pretty big advantages and possibilities, and I think it's really interesting and fascinating. And if you have any questions, I would like to answer them. Thank you.